So moving on to part 3, in this section of the presentation, I'm going to describe the development and implementation of the four-color fish assay, because I think this has really improved the sensitivity and specificity of this particular assay. So on the next slide here, you can see that based on some array CGH data, and the arrow is pointing to the profile that we saw on a typical tumor that had lost a copy of PTEN. So you can see here the ratio shifts to about 0.5, so that when the copy number plot shifts towards deletion by 0.5, this indicates an area of loss. So it starts here and moves down the chromosome to the other side of PTEN. This really allowed us to think a little bit more about optimizing the probe design so that we could include controls either side of this region that seemed to be fairly frequently lost in prostate cancer. So we did a meta-analysis of 117 prostate cancer genomes and did a similar comparison of the position of loss along chromosome 10 and mapped out the region which is minimally deleted. And this is an example from that study. And so essentially, as I advance the slide, the minimal deleted region is shown here, delineated by the lilac and the green dashed line, and in fact PTEN is in the middle here. So in our initial research probe design, we had a centromere probe that was this turquoise color, and then a probe A, lilac color, which in fact is the BMPR1A gene. PTEN is red, and green is the probe B, which is the FAST gene. So that was our original probe design, and we reasoned that by including these closely linked flanking probes, we could really position the area, the nucleus in the cell, and take advantage of some three-dimensional information that I'll be coming to. So using the four-color probe on cytogenetic preparations, of course, they're so close together that the colors merge, as you can see here on each chromosome 10. These are normal chromosome 10s. This is just comparing to the two-color fish assay, and you can see this big distance between the centromere and the PTEN region. If we just take a closer look at the nucleus here in this preparation, you can do spot counting, and you can see this area here is one chromosome, this is the other one, and you can see that everything's there that should be. These in fact are G2 nuclei. And so the other point was that typically when we were doing our analysis, we were using 4 to 5 micron sections. And of course, when you look at these from above, this is a two-color fish assay, everything gets flattened into two-dimensional space. So this is a movie that, in fact, I'm just showing you some freeze frames. So we're just going through the section to look at it along the axis. So this shows looking into that 5 micron section, a bit like you're in a fish tank. Looking along, and you can see that the position of centromere and PTEN spreads right through that section, and of course one gets these truncation effects here and here, which can lead to losses that are really related to sectioning rather than actual deletion events. And this was the key, I think, advantage to our four-color fish assay. And one way that a good metaphor that I've used in talks like this is some apples that I cut in my living room here. You can see them, and this is about the same as one gets with a 5 micron section and prostate cancer nuclei. So that about 10 to 20% of nuclei have these pieces cut across, which you can't really see unless you look along the side. If you're looking from above, you can't tell. So that if you were looking at this nucleus using a two-color fish design, you could score this as being a loss. In fact, because we have these flanking probes, we have a better idea as to what's going on. So if the reality of the situation is like this one shown here, you can see that the flanking probe's presence gives you a clear idea that you've lost PTEN on this chromosome is okay. So this introduction of these control probes either side of the gene increases the specificity of the assay for detecting real PTEN deletions and discriminating them from these kind of truncation effects. Okay. We did some analyses where we looked at normal, undeleted nuclei of a similar diameter to prostate cancer. We used BPH, comparing 2-color fish to 4-color fish. And this is the frequency of losses you see with 2-color fish. About 12% of nuclei have lost 1 copy of PTEN just by virtue of truncation. In the same sections, using 4-color fish, something like 4% of nuclei have lost 1 copy of PTEN because of truncation. So it really does increase one's specificity for detecting these types of events. Now, some laboratories may use thinner sections than 5 to 4 microns, in which case, of course, it's necessary to have appropriate controls where you measure the background truncation effect and set your thresholds accordingly. So if you're using a slightly different kind of configuration with 4-color fish, it's important that you have appropriate controls. And of course, one always has to do the analysis in an area where a pathologist has circled regions of cancer. I'll say a little bit more about some of these quality things later. And so the actual assay that we developed and used in our research is shown here. So in the normal pattern has the 2 centromeres, and in this case PTEN is red, and then the flanking probes are lilac and green. That's not deleted. This one has 1 deletion, and in fact the deletion involves the red PTEN gene and also probe B, which is green, so you don't see either of these two on this chromosome. This deletion, in fact, is homozygous, so both copies of the chromosome 10 have lost PTEN, but they've only lost PTEN, they've kept probe A and probe B, so you see the lilac and green in both arms. Now, I'll say a little bit more in the next presentation about interpretation of the assays and how we've been using it. So if you're interested in this, please move on to the next section. Thank you.